Hello, hello. My name is Evan Forbes. I'm with Celestia, which is the first blockchain network. And on Celestia, you can build whatever. So if you're interested in anything that I talk about in this talk or in my work in general, you can find me on Twitter. I'm Evan S. Forbes on Twitter, or on GitHub, I'm just Evan-Forbes. And today I'm going to talk about trust minimized and impact maximized rollups as a service. And the thing, I might get a little opinionated here, a little political maybe even, but I hope that adds to the spiciness and like maybe just the general entertainment that we can get from this talk. And the entire thesis is, with this trust minimized portion, is that sovereignty, not just sovereign rollups, but sovereign blockchains in general, are actually the difference between what has come before us with like banks, governments, Web 2, and crypto. I know that's a little spicy, but I do think that there is some truth there and there's some value there. And I think if we critically think about it, we can design rollups as a service. We can design these services that help build these rollups and do so in a trust minimized way. We can preserve that property and perhaps unlock something really, truly special and get to some insane, crazy properties that I don't really think have ever existed before, that's really exciting. So anyway, the first start answering that question is we can get to what actually makes blockchains compelling. What actually makes blockchains special? Not necessarily the protocols built on top of the blockchains, but the blockchains themselves. Why is Bitcoin special? Why is Ethereum special? And I think it comes down to sovereignty, where the ability to verify, right? Don't trust, verify. The ability to verify these chains. I can verify Ethereum on a laptop. On Bitcoin, it's probably something even significantly smaller. I can choose the rules that I follow. I'm not trusting another committee, right? We're building a network from the ground up, and we have this like sort of crypto anarchic promise and this like property that is to build a network, to build a structure that is resistant against abuses of power and hierarchical structures. That's crazy. That's a really special property. And right, and the title of this talk, Impact Maximized. We don't want to just do the same things that we did before. We don't just want to have the banks, but faster and a little bit more decentralized and a little bit more permissionless. That's good. Having these permissionless, decentralized systems is really good. But if we're still trusting committees, if we're not actually verifying, then we're not the ones who are choosing the rules, right? We choose the rules that there's only 21 million Bitcoin. We choose the rules and we enforce them for Dogecoin and for Ethereum and for all of these other blockchains. We enforce the rules. And I think that's what makes things special. So when we're designing rollups as a service, how can we even capture that? How can we amplify that? And so to get to more of like this sovereignty portion, I think Mustafa Al-Bassam, he's the CEO of Celestia Labs, co-founder of Celestia Labs. He's done a lot of work. There's a paper published, Data Availability and Fraud Proofs, and of course, Lazy Ledger, which is now Celestia. And he framed this, I think, summarized it perfectly. Sovereign blockchains, not just rollups, not just modular blockchains, sovereign blockchains allow people to create social contracts and enforce them directly without going through any intermediary. Top-level social contracts, right? This is a crazy thing. This hasn't existed before. This is the new thing of blockchains. This is the thing that makes them different from what came before. We should amplify this to really create compelling services for rollups. And being able to verify the chain choosing the rules ourselves, sovereignty, being able to hard fork. This puts people over tokens, people over validators, people over governance, right? This property is really something truly special. It's not just token holders who get to make a decision. It's node operators, people who are verifying the chain. And to better answer this question, we can even ask, like, why do banks and governments suck? Why does BlackRock suck that BlackRock owns everything? And this funny cartoon of this Futurama representation of Richard Nixon, who is known to abuse powers, right? Why do blockchains suck? Or why, sorry, not blockchains. Why do governments and banks suck? And it's mainly because we can't really pick the rules. And these banks and these governments, they have monopolies. They get to decide what actually occurs. Now, in theory, it's like a democracy and people get to decide, right? But in actuality, things start to get messy really quick. I mean, just like go look outside. A lot of the reasons why a lot of people are attracted to the space is because they are so easily disillusioned with how the current system works, right? I don't really need to explain it. Satoshi didn't, when they made Bitcoin, their whole idea was to make a currency that was controlled by people, right? This crypto anarchic property, and their social contract is 21 million. It's only ever going to be 21 million, right? Seems in the world, right? The Fed has this infinite amount of money. Can I pause this now? Oh no. The Fed has this infinite amount of money, right? They can do whatever they want. They can enrich themselves in theory if they want, or they can design whatever type of society they want, and we don't really have a say. So then this is this whole meme of like this money printer and everything. That's what Satoshi was going against, at least I think. And I think it just reset the talk. No, I think I just had duplicate slides. Sorry about that. Okay, so what actually makes blockchains compelling? That meme, I think, summarizes it up sort of, is that we can go against that. We can design our own money. If we want to print money, though, we can. That's the crazy thing. It's like the rules are arbitrary. They're programmatic. We get to pick them by verifying the chain. So this is where modular blockchains come in. This is where rollups come in. Is rollups make it orders of magnitude easier to verify the chain. Orders of magnitude. This is what DA and rollups solve. And they do this in a trust minimized way. And right, this enables two things. This enables sovereignty, which is fundamentally derived from verifying the chain, right? Sovereignty, the ability to hard fork. We pick rules, node operators, and in this case, with modular blockchains, light clients pick the rules, right? I can run a light client on my phone. I can verify the chain. I can pick the rules and the result of those rules, right? Not just the rules, the result of those rules from my phone. And people all over the world can do that. That's the crazy thing. That's sovereignty. And security, right? Normally, when we think about proof-of-stake blockchains, we think about committees of validators. Well, guess what? Getting committees of validators to operate in an honest way is very difficult because you have to stick enough capital in there in the blockchain and lock them up and have it socially slashable. It's still secured by social consensus, but it's socially slashable funds. Those funds have to be larger than the funds that are in the blockchain, kind of, because otherwise, if it's more profitable to attack the blockchain, it's like, ooh, that might actually happen. So that's why it's like, this is a really difficult property to get committees to actually behave honestly. That's why we use proofs instead. With modular blockchains, we use proofs. Committees are expensive. Proofs are cheap. They're also sovereign, and they're also extremely secure, right? Validators are cucks. The security of the chain comes from proofs. That's the beauty of like modular blockchains and rollups as a service. right? Rollups and modular blockchains are this powerful thing, but they're still missing a lot of pieces. That's where this rollups as a service comes in, is this sovereignty, the security without compromises. We can, because the systems and how they work now, there's still like a lot of gaps. Like, how do I have decentralized sequencing, for example? Like there's just a lot of gaps still. And we can develop these services that still preserve the fundamental things that make rollups so special. And when we do this, we always have to think about things from proving from a light client perspective, right? All of this comes from the ability to verify the chain, in theory, from your phone, using some sort of light client. Just a light computer, really. But anyway, the point being to be able to verify the chain, okay? That means that everything that we think about, everything that we design has to be in those terms. How can I verify this using a light client? Honest majority assumptions are icky. Light clients, if they have to make an honest majority assumption, lose their security. They lose their sovereignty, because now it's not trust, don't trust, verify. Now it's don't verify, trust. It's backwards. That's what happens when light clients have to make an honest majority assumption. We don't want that. We want validators to be cucks. Okay, trust minimized DA. This is harder than it sounds. I work at Celestia. I'm one of the core developers at Celestia, so I have a little bit of experience in building some of these systems. And trust minimized DA is harder than it sounds. For one, we have to have DA sampling. Okay, that's cool. I think most of us have a general idea of how that works. And then you have to have enough samplers, so you have to have enough network effects. You have to be convinced that there are enough other light clients sampling that you can reconstruct the block only using light clients if need be. Okay? Then you have to be convinced that the error-sure encoding is done correctly. Okay, so we use fraud proofs for that at Celestia, but other chains you can use KZG commitments, you could just prove it in a ZK way. And it's not that, to be clear, Celestia could use those other mechanisms as well. Right now, fraud proofs, they're very simple, they're very easy, they're extremely easy to audit. They use normal cryptography that we've been using for 20 years, and they're extremely scalable. We can have very, very large blocks, unlike those other mechanisms, unlike the other ZK mechanisms, but not to get too distracted with that. There's also this thing that I'm pretty sure no other blockchain has, which is cheap inclusion checks. So it's great that, as a light client, I sample the block. That's great. I'm convinced it's available. I'm convinced the error-sure encoding was done correctly. I'm convinced that there's enough light client sampling that we can reconstruct the block if we need to. But what happens if, now I still have to be convinced that the data that I care about, the rollup header, it has a hash, it has a commitment over some block data. How do I know that that block data is actually included in the DA block? That's kind of an important thing, right? Otherwise, none of that other stuff matters. None of it matters. It only matters if the data that I care about has been included in the block. How do you prove that? Well, typically, that's done using a Merkle inclusion proof. Okay, well, if we use Merkle inclusion proofs, what's the problem there? That requires you to download the entire block. Like, the entire point of a light client is that it doesn't have to do that. So you have to have significantly cheaper ways. And we actually do that in Celestia. So in Celestia, we instead of having to prove inclusion to the entire block, we prove inclusion to just the transaction that pays for that block. So apologies, I didn't really have a lot of time to put together these slides or a lot of visual aids, but you can see this is sort of how we organize the original data square in Celestia. At the top bit, we have this transaction portion. That's where all these transactions go. It's very small. I can prove just a single transaction was included. And that is good enough to convince me that the blob, the message, the rollup block for that transaction was also included in the same block. And we do that by getting a little bit clever. There's more information on this in our specs in the data square layout. I think like the rationale for this, of how we actually do this, but effectively, that commitment in the rollup header, we changed the way that we create that. Instead of just using a normal Merkle root, we use a Merkle root over subtree roots in Celestia. Because now, if you can find those subtree roots and you prove inclusion to those subtree roots, that's just the same thing. Because as a rollup light client, you don't care what the actual data looks like. You only care that the commitment that is in the rollup header has been included in Celestia. And because we have this, we have a special type of fraud proof that proves that some given transaction was included that pays for a block versus the actual blob in the block. We prove that if one is there, the other also has to be there. I won't go too much into how that fraud proof actually works. Again, hopefully by the time this video is published, our specs have been updated and all that information is there. You can find that if you just go to the Celestia GitHub, go to Celestia app, and then go to the specs. Sorry, again, I kind of had to throw these slides together rather quickly. And so we have trust minimized DA. Another thing that we need is that for rollups to be this magical dream of rollups as a service where I can just in one click deploy my own sovereign rollup, is I also probably want it to be decentralized. I want it to be censorship resistant. And shared sequencers are a way to do that. They're a way to scale that property. Because if we think about it, like if we have like the normal sequencers, we have to have a committee create the blocks if we want it to be censorship resistant. Or we can have backup mechanisms too, where I can force inclusion using the DA layer. That's a very good option as well. But if we want like the liveness properties, if we always want our rollup to be alive, then we also have to have some sort of committee. So, but the idea behind shared sequencers is what if we can share that committee, right? So I've been thinking about how do you decentralize this? How do you decentralize the liveness properties, the sequencing of rollups since about last summer? I went through a few iterations, spoke with a lot of folks at Celestia, and eventually on winter break, I finally had time to write it up. And I wrote up this forum post. It's called sharing a sequencer set by separating execution and aggregation. If you're super interested in that thing, I would highly recommend. Well, I guess that's tooting my own horn. Just go. It's a kind of hopefully okay description of this thing. It's not formally defined. Espresso Systems has also since published I think, more thorough explanation of these things. So you can also go and find their documentation as well. But again, the idea of this is rather simple. It's like we have the sequencing, we do that all combined, and then we actually do the execution later. So in my forum post, I referred to this lazy execution, right? We agree upon the transactions first, which transactions have to be included. Note, not their order, just the transactions that have to be included, and then we execute them later, and then we actually do the proving. So this changes the proving a little bit, and I haven't, again, we're shipping mainnet. We've been really busy, so I haven't really had a chance to write up how this actually changes proving. But there's other people at Celestia, well, notably Gabriel, who has been helping me like sort of ideate around what can you actually do now that with like this lazy proving, right? So to get like a slightly better view of what a shared sequencer can do, the users, they submit their transactions or bundles of transactions directly to the shared sequencer layer. The shared sequencer layer can produce blocks as fast as they want. They don't have to wait on the DA. They don't have to wait like that 15 seconds or so for the DA. They can get this soft finality. So it's obviously not as good as firm finality, but it's pretty good. It's sort of like this gradient of trust. Like whenever the shared sequencer network gives you the soft confirmation. You sort of just treat it as a soft confirmation, and you can it's enough to at least update the UX very quickly. So you can have these soft, very fast confirmations. I don't really have to deploy my own sequencer set. This is incredibly easy. Like, I just define a state machine and like define a chain ID. My users just start using that chain. And then this is an important bit, the shared sequencer part, the shared sequencer network will post the entire block data to the DA layer. And this is sort of how this is the key factor of how they actually maintain trust minimization. Everything works the same as if a singular rollup was posting their block data to the DA layer. Everything's the same there because the shared sequencer is posting all of the block data at once to the DA layer. They're the ones paying for it. How you actually pay for gas for that can be kind of arbitrary. Ideally, it's done in the native DA token, but I think I'm getting distracted. So to elaborate more on this lazy execution, again, users can submit transactions. They get these fast, soft confirmations. They don't finalize the state yet, but it's usually good enough to update a UX, at least get that green check mark, get that dopamine hit, and then we actually post the DA layer. And then as soon as the DA layer has confirmation, as soon as we have that light client verification that I was talking about earlier, where the data was actually included, on Celestia or on the DA layer, now we have firm finality, which is kind of cool. Another really cool thing about shared sequencers is they have these validity rules that unlock powerful cross-chain MEV primitives. So this thing is like, I've kind of always thought about shared sequencers as this way for MEV searchers to use as tools to sort of build blocks in more or less a decentralized way. Now, I'll touch on that more later. That full picture is not painted yet. There's still like a lot of work to be done there, but I do actually think that it's possible. So stay tuned for that. But essentially, right now, all you really have is proofs of inclusion. So you do not have atomic execution. You only have atomic proofs of inclusion, meaning I'm only guaranteed that if I have a transaction included on rollup A, I also get a transaction included, not executed, included on rollup B. That's it. It's only proof of inclusion. But you can get more creative with this. This is by block validity rules. I can say on the shared sequencer layer, I can define as a block validity rule that these specific transactions only get included if they're included at both the top of the block, or one is at the top of the block, right? And that's sort of like a really powerful, again, these block validity rules that you can include with shared sequencers help. They're tools for building out more and more decentralized block building. At least that's my hope. But anyway, that's shared sequencers. And from like a rollup as a service mechanism, I think that they're very, very powerful because they sort of give us this opportunity to think about like the services that we provide. Rollups can pretty much do everything on their own. And we want them to do that. We want rollup developers to be able to encode their own rules. However, we can start to add committee-based services to the shared sequencer. So things such as committee-based IBC, you could have a settlement layer. Committee-based IBC, you can have threshold encryption. So Fairblock just posted a forum post on Celestia that was really interesting, and they effectively do the same thing, right? You have a committee that uses threshold encryption that is also a shared sequencer to provide these trust minimized services to a rollup. And oracles, you can have socially slashable oracles. Hopefully I'll have time to talk about that later, but maybe not. And then what we're going to talk about next is censorship resistance per block. So I kind of hinted at this before with shared sequencers, but with MEV, it's effectively like you end up with one block builder. So you have a shared sequencer, that's great. And you have and that shared sequencer provides all the inclusion guarantees for all of these different rollups. But the problem is the number of rollups that can go on a shared sequencer is technically unbounded. Ooh, and that means that like a block builder for that shared sequencer is going to have run rollup full nodes for all of those full nodes. Unbounded is that's a bad thing. It's not good. And effectively, like that's a very centralizing force of having to run all of these full nodes, and like having one giant block builder, it's not very decentralized. It's not very good. So what are some things that we can do around that? So again, we're designing these services for rollups. What can we actually do? So again, like one of the underlying issues here is that I have a politician here, but you can think of a politician and a validator basically like the same thing. They're analogous at the very least. And these politicians and these validators, they have monopolies over specific things. In the case of a validator, when it's your turn to create a block for most consensus protocols, most consensus protocols in use today, that is, you get to pick everything that occurs in that block. And you can abuse that power by taking a bribe to include other things, right? We, as delegators, delegate to you, a validator, and then now that power that we gave you, you can abuse by enriching yourself, by like taking these bribes to sort of order transactions in a favorable way or censor different rollup blocks. And that's incredibly problematic when with rollups, we just want to be able to define these simple fork choice rules. But before I get into fork choice rules, we'll go to the next slide, which again, this is showing the point with these modern systems, these modern blockchain systems, a lot of the times so far, the validators, the politicians, they're the ones who are getting rich. They're the ones who are taking all of this money. And then the users of the chain, that's a downslope, right? And the network isn't making money in most of these cases. For Ethereum with EIP 1559, arguably you're getting some increased burn rate, which in that case, the network is going up quite a bit. But anyway, without breaking this proposer monopoly, right? Without breaking this proposer monopoly, we're kind of stuck in this boat. We're stuck in not being able to define where the profits of a system get captured. So thankfully, earlier this year, Duality, the folks at Duality, including Elijah, who wrote this paper, and this is a screenshot of a forum post on Celestia, describing exactly how you actually could do this. And this is the key thing for not solving MEV, but being able to programmatically define where the profits of an entire system go. And they do that by breaking the proposer monopoly. So I'm quoting Elijah here. I thought this meme was absolutely hilarious and so perfect because it's like people protesting and the proposer monopoly. And it's true. It's really true. So I'm running out of time here. I'm going to have to rush through some things. Fork choice rules. Rollups can define their own fork choice rules. If you can define your own fork choice rule, that means that you can define things really simply and elegantly, like I want my rollup to, the block that wins is the one that brings the most values to LPs or burns the most of my rollup token. I can define those simply if and only if the proposer does not have a monopoly. Because if the proposer has a monopoly, they're just going to be able to pick the correct block that gets in, the block that they want, the block that they get bribed to most. We don't want that. That ruins the property that we want, right? We want to programmatically capture the entire profits of a system. I think I only have 30 seconds left, so I'll touch that we have decentralized block building. Stay tuned for that. I think there's some exciting things, lots of work, none of it's set in stone. This is just me writing things. I do think with shared sequencers we have a potential like awesome thing. And with Oracle's there's some things with ABCI++. You can have trust minimize, or you can have socially slashable oracles, which is really cool. And that's my talk, trust minimized and impact maximized rollups as a service.